Okay, so 30. Okay. Okay, so I start by doing the customary thing, thanking the organizers for organizing this one and asking me to give a talk, especially Raphael and Abhishek for inviting me to come here. So what I'll do is, I come from TIFR, Mumbai, so I want to talk about a work that I did with my PhD student, Anish Acharya, and this is the reference. And the talk has to do with resetting. I guess Debraj, my former PhD student, touched upon this topic a little bit yesterday. So I'll take it up from there or maybe start from scratch. But anyways, let's. Okay, so this, what is this stochastic resetting? So it's an emerging theme in classical statistical mechanics. And in recent years, it has started to get explored in the quantum domain. But in the classical literature now, it is almost like a paradigm, this topic of stochastic resetting. So what I'll do is that I'll introduce it in the context of the simplest possible stochastic process, which is this Brownian motion. Of course, it generalizes to more complex situations involving one and many particles and so on. So what's the game? The game is the following, that you have a Brownian motion, and we all know, I guess, what a Brownian motion is, excepting that this Brownian motion is somewhat special. We don't let the Brownian motion do its motion, all the time. So what it does is that, so this is the update rule. So xt plus dt is the position of the Brownian particle at a time t plus dt, given that it was at some location x of t at time t. So you have two possibilities. Either you let the particle do its normal Brownian motion with the probability 1 minus r dt, or you reset it to a given location. Okay. So more precisely, here is a cartoon that I stole from this original paper of Martin Evans and Satya Majumdar. So what's a game? The game is the following, that here is my space and here is my time, and I let the Brownian motion start from a location x0. I let it, like evolve according to the rules of the Brownian motion for a random time, after which I reset it. That is, I start afresh, I bring it back to its initial location, and I keep doing it. Like again, it starts from this location, and it does its bare dynamics, original Brownian dynamics for some random time, and again it is reset to its initial location. So these times, the times after which the particle is reset to its initial location is those times are random variables taken from an exponential distribution. Put it differently, at every time state there is a certain probability that the particle evolves according to its own original Brownian dynamics, and with the complementary probability it resets to its initial location. The interest in resetting, or the reason this resetting was introduced in the first place, was in the context of search processes. And the problem is the following, that suppose you have a stationary target or something that you want to look for, you want to search for. So let's say you have a stationary target and you want to know, when do I get to that target for the first time? And once I have gotten there for the first time, I found the target. Okay. So in terms of in the language of Brownian motion or stochastic processes, I am interested in the first passage time. When do I first pass through this fixed location? When do I do it for the first time? And more precisely, I will be interested in the mean first passage time. Why do I need to take the mean? Because as you can understand, in this process, there are two sources of randomness. One is, of course, the inherent Brownian randomness. And the second one is that once in a while, that is after a random time, I'm bringing it back to its initial location. So there are these two sources of randomness, and therefore I need to average over these two sources of randomness. And that's why I should be interested in the mean first passage time. What is the average time that I take to pass through this location for the first time? And the interest in this resetting arose primarily from this observation that if I plot this mean first passage time as a function of the resetting rate r, then of course there are two limits in which I know the answer. So one is when r goes to 0, that is when there is no resetting in the dynamics, the particle is following its bare Brownian motion, and then if I ask what is the mean first passage time, it's a classical result that the answer is infinite. I would take on the average an infinite amount of time to get to the target, simply because there will be some trajectories that would happily take me to the target, but there would be happily a good number of other trajectories that would take me away from the target. So the mean will be infinite. So when r goes to 0, this is supposed to be the 0 of this r axis, the mean first passage time is infinite, and the other extreme case is when r is infinite, when the resetting rate is infinite. As you can see from this figure, if r is infinite, that is, if you reset almost every now and then you just don't allow the particle to access the space. So, and then of course it would take a very long time to get to the target, because you are not just allowing the particle to move away from its initial location. It just remains confined to its initial location, more or less. And that in that limit also, the mean search time or the mean first passage time is infinite, and therefore it is evident that when you plot it as a function of the resetting rate, there's going to be an optimal value of the resetting rate at which the mean first passage time takes up its minimum value. That is, this protocol gives a way to find a misplaced target in the shortest time possible, in the way that I just mentioned. Okay, so this was primarily the reason for introducing this, and over the years this resetting has been this paradigm of resetting has been explored across domains in various fields and so on and so forth. And in particular, it leads to very novel non-equilibrium stationary states, and it leads to a large number of very interesting static and dynamic properties. A few years later, 7 years later, this classical thing was generalized to the quantum domain, where you do the kind of the equivalent of what you would have done anyways, which is the following: that you take a quantum system which evolves according to some Hamiltonian h, and what you do is that you let the system, the wave function of the system, the wave vector of the system, like evolve according to its original dynamic Schrödinger equation with probability 1 minus r dt, while with the complementary probability r dt you reset it to its initial form or a given form. Okay, so this is kind of the equivalent of this one. So the main thing to note, or the main message to take away from this slide, is that in these cases resetting is unconditional. What do I mean by it? What I mean is the following: that when you reset, for example, when you are resetting to x0, you don't care where you are. You could be very far away and yet you reset to the same location, or you could be very close by and still you reset to the same location. So your current state is immaterial. It doesn't matter what you are doing right now. Somebody has just mandated that you have to reset to x0, and that's what you do. Okay, so in that sense, resetting is unconditional. You reset to a given state irrespective of the current state. Okay, so this is just because there were so many people working, who have been working in this field, that I thought that maybe this is a way to, not to, or, in case I forget someone, so you keep searching for your name while I move to the next slide. So these are the people who have worked on, resetting, and there is a very nice review by Satya and others, written about 5 years ago. So you can find a lot of applications and techniques and this and that in this review. Okay. So the purpose of this talk is to tell you what new features come in when you do conditional resetting. So by conditional, what I mean is exactly what I meant, what I showed in the slide just a while ago, namely that in the usual resetting case, what you do is that you reset independent of your current state. And in conditional resetting, as you may imagine, you reset to a set of states or to one state conditioned on the current state. So where you are decides which state you are going to reset to. And of course, this is a game that we are not playing for the first time. This was first explored in this work by Perfetto and others, Lezanovsky and others in 2021. So the game that they played was in the so the game that they played was in the context of the paradigmatic transverse field Ising model. So as you all know, the transverse field Ising model has this Hamiltonian. There's an XX coupling and there's a magnetic field in the Z direction. And so this is the X magnetization, and okay, so people are having fun in my lectures. Good. Okay, so what you do is that, so in this case, of course, I mean, the game is the same, that after a random time you decide to reset, but then the way resetting is implemented is in the following manner, that what you do is that after a random time, you measure this magnetization, okay? And if the magnetization happens to have a positive value, then you reset to a state in which all the spins are up in the X direction, while if you happen to get a negative value of the magnetization, you reset to a state in which all the spins are pointing in the down direction. So therefore, the state to which you reset depends on the magnetization value at the moment you decide to reset. Okay? And of course, this is conditional by definition. And what they showed, and this is something quite remarkable, what they showed is that, I mean, they were plotting this magnetization square of the system in the stationary state of the system. So as can be like argued, whenever you are resetting in the dynamics, the stationary state turns out to be not an equilibrium but a non-equilibrium stationary state. That's why you have this NESS here. So what they showed is that, I mean, if you did not have resetting, then we know that there is a quantum phase transition as you tune the value of H across a critical value HC. But then when you turn on resetting, then you find signatures of the quantum phase transition as a crossover between a ferromagnetic and a paramagnetic phase. So resetting, I mean, drives the system into a non-equilibrium stationary state, and yet you retain some of the features of the Bayer dynamics, especially signatures of the quantum phase transition of the Bayer model. Okay. Yeah. So in this context, the reason we decided to work on this tight binding model was the following, that of course we are also interested in conditional resetting, but then we want to ask the following question. Yeah. No. So this one is the critical point when there is no resetting. And of course, this one will depend on the resetting rate. You mean the curvature? That depends on the resetting rate. Yeah. Yeah, because there is a question of competition between two time scales, and yes, of course. Yes. So in the conditional resetting study that we embarked upon, so we want to ask the following question. So first of all, we want to reset to a set of states, and the choice depends on the current state of the system. But then we ask the following question, that what are the effects of conditional resetting when the Bayer dynamics does not have a steady state by itself? See, in the case of the transverse field Ising model, the model itself had a steady state, and of course the nature of the state changes when you introduce resetting. But suppose you did not have a steady state to start out with, is conditional resetting enough or sufficient or necessary to induce a stationary state in the system? That's one. Secondly, is it always so that you always have a steady state when you have conditional resetting? And what is the nature of the what is the nature of the steady state that the system relaxes to? And can one characterize it analytically? I'll show that what will happen is that in this case of conditional resetting, when you write down the time evolution equation for the density operator of the system, you have a Lindblad kind of dynamics, excepting that the evolution is non-Markovian. So it's not quite Lindblad-like. I'll like elaborate on this as I go along. So these are the primary motivations, and we chose to work on address these questions in the context of the tight binding model, which is the simplest scenario that one can envisage in order to address analytically the questions raised. So tight binding model, I guess I don't have to introduce, but anyways, let me introduce, which is the following, that you have a single quantum particle, which is moving on a one-dimensional lattice that extends all the way from -infinity to +infinity. And what does the Hamiltonian do? It just tells you that the particle is going to hop with a certain probability to the right neighbor site and the left neighbor site, and gamma is the tunneling probability or the hop probability. And since it's a single particle problem, it can be solved very easily by going to the Fourier space. So the main result that emerges, I mean, these are like classical results, so I'm just summarizing. So the main result that emerges is the following, that suppose you start the particle from some location n0 and you ask, what is the probability at time t for the particle to be found on any given site m? Okay, so what is going to happen is that, this is a caricature of the dynamics. What is going to happen is that you let the particle start at t equal to 0 from a given location, let's say at m equal to 0, and as time progresses, the particle is going to spread out over larger and larger number of lattice sites, and that shows up in this figure as the, as in the following manner, that you see that this probability at 0 is decreasing while it is picking up at other sites, and that manifests in the mean square displacement of the particle. Of course, the average displacement is 0 by symmetry, but then the mean square displacement, if you compute, you find that it just grows unbounded in time, quadratically in time. This is because, I mean, there's nothing to kind of bound the particle, so it just goes, and spreads over larger and larger number of lattice sites as time progresses. So this is the tight binding model, and this is the conditional resetting thing that we are going to implement. So let's see what we are doing. So this is my lattice and this is my time. So what I do is that, so this is my like location of the particle at time t equal to 0. So what I do is that, in the same manner as Perfetto et al. Were doing the conditional resetting, they were measuring the magnetization and resetting to either this state or that, depending on whether the magnetization is positive or negative. In the same manner, so what I do is that I ask at any given instant when I decide to reset, and of course I reset after a random time, tau, taken from, let's say, an exponential or a power law distribution. Whatever it is, whenever I decide to reset, I ask, what is the total probability of finding the particle to the right of the origin and to the left of the origin? And then I have two reset sites, which I denote by NL and NR. So what I do is that I decide to reset to a site NR to the right of the origin, depending on what is the current probability of finding the particle anywhere to the right of the origin. So when I decide to reset, what I do is that I find what is the probability of finding the particle anywhere to the right of the origin. I find that probability, and with that probability, I reset the particle to site NR. And I do the same game for the site NL. That is what I ask, what is the net probability of finding the particle anywhere to the left of the origin. I find that probability, which is this quantity, and I reset to NL. Okay. So this is a kind of a time evolution. So what I do is that I start from N0, I let the system evolve. So since the particle is starting from one site, and then I let the system evolve according to the Baire dynamics, the particle is going to spread out over the different lattice sites. And then let's say at time t equal to t1, I decide to reset. So I find out what is the net probability of finding the particle anywhere to the right of the origin. And with that probability, I bring the particle to this site NR. And similarly, I find out what is the net probability of finding the particle anywhere to the left of the site. And with that probability, I bring the particle to the site NL. So post reset, the particle, with some probability will start from site NR and NL, okay? And the process continues. I just keep on doing it, okay? So this is conditional in the following sense, that the probability with which I reset to site NR and to site NL depends on what is the probability of finding the particle at that very instant to the right of the origin or to the left of the origin, okay? I hope the protocol is simple enough. So this is the probability. How do I find the probability? So what I do is that, suppose I want to know what is the probability that I reset to site NR starting from site N0. So what I do is that I start from site N0, I let it evolve for time tau 1. Let's say after time tau 1 I reset. So this is the unitary evolution. I take its overlap with site J, where J can be any site to the right of the origin, and this factor is there just to make the probability symmetric with respect to the origin.
Are you, this NL and NR are placeholders that you're going to sum over the entire lattice? Or
no. So these are fixed sites. So these are parameters given to me, like NR and NL, I will choose which sites I'm going to choose, reset to. But the only thing that I need to keep in mind is that when I reset, I do it with a probability that depends on the current state of the system. So the evolution of the system, the full evolution of the system evolves much like what Debraj was mentioning yesterday, namely that I start out with a given density operator. This is my initial state. I let the system evolve unitarily for a random time, and then I do a conditional reset. So here, since the reset is conditional, it depends on the current state of the system. So therefore, the operator, the super operator that implements the resetting protocol depends explicitly on time. It's not a constant, it depends on when you are going to reset, and that determines the form of the super operator that implements resetting. So let's say this is one realization of the dynamics in which resetting takes place at time instances T1, T2, T3, T alpha, etc. So I let it evolve unitarily, then there is a reset, then unitarily reset, and so on. Okay. So like as I had mentioned here, e to the power minus LT, where L is the Liouvillean, it implements unitary evolution, while T, this super operator capital T, which is a function of T, it implements conditional resetting. There is an explicit dependence on time simply because resetting is done with a probability that depends on the current state of the system. Like as it turns out, and I will show details if I have time towards the end, you can write down exactly using the scheme of evolution given here and going to the Laplace space, you can write down the time evolution equation for the averaged density operator. What does this average refer to? I average over many dynamical realizations because there are two sources of randomness. One is, of course, the system is quantum, so it has its own inherent quantum randomness, but the second randomness is coming from the fact that over a fixed time t, when I repeat the experiment over and over again, then of course, I don't know when exactly the resetting events are going to take place. They may take place now, they may take place 10 minutes later, they may have taken place 10 minutes earlier, and so on. So there's also a classical element of randomness, and so I need to average over that. So this is the rho bar t, this is the density operator of the system. One can write down exactly this time evolution equation. So the first term, it refers to just the unitary part of the evolution. L is the Liouvillean. This is the, if I forget about this second part, this first term is just the von Neumann equation, while this second part emerges simply because of resetting in the system. What is lambda? Lambda is the rate at which I do resetting, more precisely the random times after which these resetting events take place are sampled from an exponential distribution, lambda e to the power minus lambda t. So therefore lambda is the rate at which you do resetting, or 1 over lambda is the average time between two resets. So that factor appears here, and of course if you put lambda equal to 0, you recover your like original Liouvillean equation, von Neumann equation. But the point to note is that you get these extra terms, and these extra terms, as you can see, I have written the terms explicitly here. Let's say h alpha, alpha greater than equal to 2. As you can see, if you want to know h alpha t, then you need to know h alpha minus 1 at all previous times. That is to say that the evolution becomes highly non-Markovian simply because the system retains its memory. Because whenever you decide to reset, you reset with a probability that depends on the current state of the system, and that depends on the previous state and so on. And this is quite unlike normal resetting, in which whenever you reset with a constant probability, you of course forget about whatever had happened before the reset. Okay? As I have shown here, that if you have normal resetting, that is if you have unconditional resetting, when you reset to a given state independent of the current state of the system, then the time evolution is the time evolution of the density operator follows the usual Lindblad equation, where there is no memory, it's a Markovian. While if you do this conditional resetting, you have non-Markovian evolution. And yet in this context, we are able to obtain some exact analytical results that I'll explain now. As I mentioned, I'll talk about this exponential resetting, which is the case in which time interval between reset is taken from an exponential distribution with the rate lambda. So this is, I'll just flash some of the results. For example, this is the case where you start the particle from location n0 equal to 0, that is the center of the lattice, and you reset to sites which are symmetrically disposed with respect to the origin. So the first thing to note is that, and here what am I plotting here? This is the probability for the particle to be found on like site M at time t, averaged over, of course, dynamical realization. So the first thing to note is that indeed you get a stationary state, as is evident from this figure. I have plotted Pm bar t as a function of t for two representative sites, and what you see is that they indeed relax to time independent value. This is given here, shown here as well as here. But more importantly, if I look at the stationary state, what is the form of this Pm bar t when t is very large? So t is here, I think 1000 or so. What you see is that the particle is more likely to be found at the two reset locations. You may say, well, that is quite obvious because you are resetting to these two locations. Well, you do it with a conditional probability, but yet you are, bringing the particle again and again to these two reset locations. So this is obvious, and I'll show that this is not obvious, but at least up till now it is obvious that this probability is going to be peaked around the two reset locations, okay, 4 and minus 4. And concomitantly, if you look at the mean square displacement, you see that at long times, the mean square displacement relaxes to a time independent value. So it just shows that with the help of conditional resetting, you have been able to localize the particle around the two reset locations, NL and NR. Okay? How does this, if you don't do,
conditional reset, but you just, let's say 50% probability just reset it to minus 4 and plus 4.
well, I guess, I mean, just by looking at this one, I guess you can always choose, a probability in the conditional case and the unconditional case so that they match each other. But then what will happen is that for the same set of parameters, you will get different values. You can tune the, the resetting rate in the unconditional case to match it here. Okay? But if I look at the dynamics is going to be very different because in one case you have non-mark. It's the following thing, but just by looking at the steady state, you won't be able to make out whether it is conditional or unconditional. But if you look at some dynamical quantity, you will find, for example, the relaxation to the stationary state will be different in the two cases. Okay. So this is the case, this I maybe skip, this is not very important, I guess this one is more important. So here what I do is that I choose my reset locations to be not symmetrically disposed with respect to the origin. Okay, so for example, my left reset site is at site number -4 and the right one is at site 8. And what I see is that due to this conditional resetting, and this is an effect that emerges only because of conditional resetting, that although the resetting rates are symmetric with respect to the origin, yet you get a stationary state in which you are more likely to be found on one reset location than in the other. Okay, so of course the rates are like they are symmetric with respect to the origin, but yet particle is more likely to be found at one of the reset location, namely the location which is farthest from the origin, than in the other location, that is in the reset location which is to the left of the origin. And this is quite interesting because what it shows is that there is no bias in the tight binding model dynamics. I've chosen the rates to be completely symmetric with respect to the origin, and yet I am able to induce an effective bias towards one of the reset sites, and this is only because of conditional resetting. Simply because so this is my initial location, and since one of the reset locations is closer to the origin than the other, so what will happen is that the particle will quickly go over to the other side. So there will be a higher reset probability at this site than this site. Okay. So in these cases, as I mentioned, if you do resetting, you always have a stationary state. You can play with the form of the stationary state through a clever choice of the sites to which you reset, but you always have a stationary state. And then the question would be that is it obvious that when you do conditional resetting, you always have a stationary state? And the answer is no, because suppose I play the same game, excepting that now I sample the resetting time intervals not from an exponential distribution, but from a power law distribution, which is the case here. And in this case, of course, I mean, this is one possibility. I mean, one particular scenario that we looked at. Of course, one can look at more general scenarios, which is the following, that suppose I start at site N0 and these are my reset locations, then I get a stationary state when this alpha, the exponent that characterizes the decay of the probability P of tau, when alpha is larger than 2, you have a stationary state. For example, here, you have a stationary state in which the particle is localized around the two reset locations, and again you can induce an effective bias towards one of the reset locations through the choice of the reset sites. But suppose you choose a value of alpha which is smaller than 1, that is, the power law decay is quite slow, and in this case, as is shown here, no matter how long you wait, the particle just keeps on spreading over larger and larger number of lattice sites as time progresses, despite the fact that you are doing resetting. So therefore, resetting is not able to induce stationary state in the system, despite the fact that, of course, you are bringing it like once in a while to its to the location NL and NR. While the case alpha between 1 and 2, it is somewhat tricky in the sense that in this case, you have a stationary state, but the mean square displacement just keeps on increasing as a function of time, simply because the distribution is the probability distribution has fat tails. Okay? So this is what is shown here. This is the mean square displacement for the three cases, alpha larger than 2, when the mean square displacement happily settles to a time independent value. When alpha is smaller than 1, the mean square displacement grows unbounded in time, as in the Bauer dynamics, so there is no stationary state. While in the case when alpha lies between 1 and 2, this the mean square displacement, it keeps on increasing. Of course, not as fast as in the Bauer dynamics, but still it just grows as a function of time. So therefore, the lesson to take away is that conditional reset does not always lead to stationary state. This also holds for usual resetting when you don't do any conditioning, that when you have a power law distribution, it is not guaranteed that reset will induce a stationary state. It depends on the choice of the power. So in the few minutes that I'm left with, I'll just give you an idea of how you derive the Lindblad equation and solve for the various quantities that I talked about. So what you basically do is, so this is the dynamical evolution for one typical realization. You start with rho 0, unitary reset, and so on. So you write down the average density operator rho bar of t in terms of the time evolution operator u of t, and this u of t has a form quite similar to what Devraj talked about yesterday, excepting now the new ingredient that I have is that the T operator, the super operator that implements resetting, is now explicitly time dependent. In fact, in this paper, we developed a formalism where you can make also the bare Hamiltonian time dependent. For example, you can play with Fluke Hamiltonian. And that's why I put L of t inside an integral here. This is the unitary evolution. Of course, you need to time order if your Hamiltonian is explicitly time dependent. And the way to solve it is that, okay, this has the form of a convolution. So what you do is that you go to the Laplace space. And when you go to the Laplace space, then things simplify quite a lot. So this is the probability to be on site M at time t in the Laplace space. And that you can write in terms of, whether over a fixed duration you have one reset event or two reset events or three reset events and so on. For example, I can look at this quantity Pm2 bar. So what this gives me is what is the probability that I end up in site M at time t, starting from site N0 at time t equal to 0 and in presence of only two resets. And as you can see, this is kind of like a path integral structure, that you first go from N0 to NL, and then you can go either from NL to NL or NL to NR and so on. Okay. So I don't have much time to go into details. So let me just come to the concluding slide. So what we talked about is this conditional resetting. It's different from the usual resetting, in which you reset with a rate that is independent of the current state. While here you choose your resetting probability depending on the current location or current state of the system. And well, I showed that through a suitable choice of your resetting locations, you are able to induce an explicit bias in the dynamics, although the bare dynamics did not have any such bias. And of course, as future scope, one may deal with the tight binding model in which there is an inherent bias in the system itself, and then one may ask, well, how does it interplay with the reset induced bias, and so on. Okay, so thank you for your attention.
Thank you, Shamik. Questions? There are strategically placed mics around, so yeah, could someone please pass that mic to that gentleman? Oh, there's one on the row itself, yeah. Aritra.
Nice talk. I was just curious, like you said that there are two kinds of average, right? Does this results all hold when you interchange them? Because it's, because like if you interchange the quantum and the classical average?
Yeah, because the sources are different. Like, so you see, the quantum randomness is already contained when you are describing the dynamics in terms of a density operator.
Yeah.
Okay, the classical randomness is coming just because of the choice of the times at which you do resetting.
Mm-hmm.
Okay, so therefore, the two sources are different, and one is already taken care of in writing down or characterizing the system in terms of the density operator, and the second randomness is just taken care of through these integrals. These integrals just tell you what is the probability that I'll reset now, and then I will evolve unitarily, and then again I reset, and so on.
Okay, thanks.
So the gentleman in the blue and then Archak after, or either way, yeah.
Just one question about the other work, the Carollo perfect. So they did not, so by measuring M, you mean the expectation value, or this is just a...
Yeah, this is the expectation value. It's not really, I mean, they call it measuring, but it's not like they do a projective measurement, because that would collapse the state. So this is, you just find I don't know how to implement it experimentally, but what they do is that, okay, you find the quantum expectation of the magnetization at the time instant at which you decide to reset, and you find out whether it is positive or negative, and accordingly you choose which state to start from then on.
Yeah, I mean, I guess because you are resetting it anyway, so you probably could have done a projective measurement, because you're anyway disturbing the state, right? I mean, afterwards. But
what they do is that they find the quantum expectation of the magnetization, and then they decide on,
Okay. Thank you.
Hi, Professor. Nice. Thank you for the nice talk. So my question was, since you are working with only single particle, you can't look at its entanglement. But what about mode entanglement? Is it possible to check that?
Check that meaning, see, I mean, I haven't checked it, so I don't know whether it is, I mean, in principle,
do you think
you can play the same game for a many particle system and
no, for only single particle, would it be something interesting? If
so
we look at mode entanglement.
So actually Manas has worked on this, entanglement in presence of resetting, so maybe you can give a comment.
We studied entanglement between qubits subject to quantum resetting. So that is the system we studied, and we showed that you can have enhanced entanglement depending on the resetting rate and so on and so forth. But in this kind of system, in principle, even in the tight binding model, you can study some bipartite entanglement.
Yes.
And how does that change with resetting or something? Probably it's possible, but yeah.
Okay, thank you. Thanks.
Okay, one last question.
Yeah, so here we have resetting to two sites. Like one can imagine that there is a whole submanifold of states on which one
Yes.
could basically project with some rate.
Yeah.
So, I mean, I'm just trying to think of if there is a possibility of enhancing search rates in such a scenario by projecting to some subspace, total subspace, rather than just one site or two sites?
Yeah, I mean, this formalism is, you can generalize it in many different ways, and what you suggest is, of course, one possible way, namely that this is just one way to introduce conditional resetting, and perhaps the simplest way that you find out, what is the net probability to find the particle anywhere here, and you reset this way. But of course, one can do it more. And by the way, the formalism that I talked about, which is the, the one involving this integrals and so on. Of course, this formalism is very general, and the way you implement resetting goes into the form of this operator T. Of course, so in principle, okay, this formalism will go through, but in practice, one has to find out how much can one push in terms of doing exact analytics.
So Mahesh, last question.
Sorry, last question. So instead of using origin as the reference, if you use midpoint between NL and NR as the reference, would it be boring?
See, this initial location really doesn't matter.
But then probabilities are symmetrically selected, right?
So probabilities are, so what matters is, so the initial location will not matter. What matters is how do you, which is the site with respect to which you make the
That's
probability
the midpoint,
symmetric.
if you use midpoint.
Yeah, for example, I perhaps have a, sorry, let me see. So this one?
NL minus NR by 2.
Oh, acha, NL minus NR by 2. Well, I guess one can, this analysis can definitely be done, but I need to think a little bit what will happen. If you do it, yeah, so, okay, so if it is, okay, fine. Sorry? No, it becomes unconditional only when you have like this, no, that, the sites are symmetric with respect to the origin, then it becomes unconditional. The conditioning, it just cancels out. The conditioning becomes profound when, the rates are symmetric with respect to the origin, but the sites are not symmetric with respect to the origin.
Let's thank Shamik again.